Thank you, Madam Chair, and thanks to the Hungary Prize Committee for this award. Good morning, everyone. As you already know, I'm Catherine from Passage Projects, and I'm going to present you the parametrization, integration, and buildability, the design and construction of a 50-meter span freeform roof in Bangkok. I will start with a quick presentation of Passage Projects, then I will move to the introduction to the project, loading assumptions. I will talk about the geometry and integration of the structure in its environment, the detailed structural design, and I will finish with the buildability and the conclusion. So Passage Projects, who we are, what we do. We are creative structural engineers with offices in Singapore, Paris, and London. We work on all types of projects, from residential or commercial buildings to pedestrian footbridges. And we are particularly specialized in architectural steel structures, complex geometry structures, and lightweight long span structures. Among some of the projects that we did, this is a grid shell in Singapore, a 50 to 60 meter span grid shell that we presented a few years ago at EISS, just down Marina Bay Sands for those who know Singapore. A steel and ETFE roof in Singapore as well, and a 100 meter span dome in Manila that we presented 2 years ago at EISS. And this is the Wisdom roof in Bangkok, which is the subject of today's presentation. This is an external view, and here is an internal view. Wisdom 101 is a new, high-end, fully integrated and digital mixed-use development that comprises both residential towers and commercial spaces. The center of the commercial spaces is covered by a 50-meter span steel structure that is covered by about 1,800 square meters of ETFE. It provides an aerated and relaxing space for the pedestrians. We can see here a plan view and an elevation of the roof with the main dimensions. So the span is 50 meters, the length is about 56 meters, and we can see on the elevation that the roof is spread over 3 levels. For the supporting conditions, we have 4 primary support points spread over 3 levels, and 3 secondary support points. The secondary support points are here for vertical loads only. It is probably better if we see it in 3D. So in 3D, we can see in red the primary support points and in green the secondary support points. We can see here that the space is quite constrained for the roof. Some of the main constraints that we had was first that the canopy should not clash with the facade. The canopy should be aligned with the columns along the tower. And the canopy obviously should not clash with the slab. In terms of structural design, the design follows the American code. The roof should be designed to sustain its own self-weight, the weight of the ETFE and the aluminum extrusions, which was estimated to about 10 kg per square meter. The weight of the M&E, which is lighting, fans, for example, which was estimated to 10 kg per square meter. In terms of live load, it's only for maintenance, so it's 24 kg per square meter. Wind loads were defined based on a wind tunnel test, and pressures vary from 0.5 kPa to minus 0.75 kPa, applied normal to the roof surface. Load combinations follow the American code. There are small earthquake loads in Bangkok, but they are very small and did not govern the design, so I will not go into more details about that here. In terms of geometry, so the client wanted a column-free roof, but we saw previously, and we can see on this image that shows all the towers around the roof, that it's a pretty constrained environment. So we did several iterations and studied several options in order to find a structure that best fits in its environment and with the supporting conditions that we had. So we have here 3 options that we studied at early stages of the design. we wanted to have a roof that was elegant and that provided a sense of relaxation, basically, for the commercial spaces. So option 1 is obviously not very elegant, so it was quickly eliminated. Option 2 presented, let me try to see if I can make that work. Yes. So option 2 presented a kink in the surface around here, because we were trying to connect to the mid-level support. So the kink was not very pleasant architecturally. Option 3 consisted of keeping the same kind of system than option 2, but introducing a column which enabled to keep the surface reasonably smooth and elegant. So this was the option that, that was adopted. So the surface is inspired by a paper fan. It's divided into 18 strips that form the ETFE cushions. And these 18 strips are supported on 17 arches, which themselves are supported on edge beams that spread back the loads to the supports. 15-meter span long cushion can be a bit long, and so in case of damage of a cushion, it could pose a risk of operations of the mole while we wait for a replacement of the cushion. So we suggested that these long ETFE cushions were divided into several cushions in order to reduce the risk for the client and to facilitate the replacement in case of damage. We can see here the cushion layout, and longitudinal beams between the arches were added in order to divide the cushions. So we can see here in 3D, we have the longitudinal beams that were added between the arches and the edge beam. Of course, the longitudinal beams have a second purpose. They provide a restraint for the arches. So in Thailand, rain events can be pretty heavy, so you need to have a gutter in order to avoid water free flow in the commercial spaces. So we needed a gutter around the roof, which means around basically the edge beam. The gutter dimensions were defined by the M&E engineers to be 800 millimeter wide by 250 millimeter deep. And the roof was treated as an architectural feature. So we want the gutter to be treated as an architectural feature too. For that, we studied several options. The first option was to have a cladded aluminum gutter. This is basically a traditional gutter design. We have aluminum gutter connecting to the edge beam. In order to keep this nicely architecturally, the gutter would have to be cladded, and this cladding would have to be segmented. So, well, first, the segmentation would not be so nice, and secondly, it would have a lot of joints, which then would present a risk of streaking during the long term, which would not be very pleasant architecturally. The second option was to have a steel gutter connecting to the edge beam. So the steel gutter would have roughly the same shape as an aluminum gutter, but it can be curved and it does not need to be cladded. But imagine we have an edge beam that spans between 25 meters to 50 meters that supports the load from arches which are 50 meters span. So the edge beam is already quite big. And next to it, you add a gutter that is already 800 millimeter deep. So the whole buildup of gutter plus edge beam would have to be quite big, which would not be very elegant. So the third option that we considered and that we chose was to integrate the gutter in the edge beam. So for that, basically, it was to do a steel section with basically 2 ears protruding out of the section and creating the gutter just on top of the section. Because this section is quite big, we've decided to use pentagonal sections that translates into a language of lines, which is basically a bit more elegant from an architectural point of view and looks a bit slimmer than if it was just a really fat section. I said previously that the longitudinal beams provide a restraint for the arches, but additional bracing was required to restrain properly the arches. We have decided to use tension rods in order to keep the structure reasonably light-looking and to facilitate the installation. So we have studied several bracing patterns. So 4 of them are shown here. The first one is to have a bracing that is parallel to the longitudinal beams. The second one is to have a bracing orientated at 45 degrees from the longitudinal beams. Third one is the other 45 degrees. And option 4 is to have the two diagonals. Option 4 would require twice the number of tension rods and twice the number of connections. So from a cost point of view, that would be more expensive, so we decided to quickly eliminate it. We've done a comparison between the structural efficiency and the elegance for each option. The roof design is governed by deflections, so structural efficiency was measured by comparing the deflections of the roof under wind load. We can see here some analysis results of deflections under wind load for the three options, and a comparison table with results for each bracing pattern. So the option 1 has a good structural efficiency and the best elegance. Option 2 has the best structural efficiency and a medium elegance, and option 3 was quickly eliminated because it has a medium structural efficiency and a medium elegance. So the question now is which option to choose between structural efficiency and best elegance. Option 2 was only 20% more efficient than option 1. So we decided to choose option 1 because it was the best compromise between structural efficiency and elegance. Global stability of the roof was checked with Eurocodes because it gives a little bit more detail than the American codes for such structures. So a linear buckling analysis has been carried out to find buckling modes with buckling factor lower than 10. And then a geometrically nonlinear analysis with imperfections included was carried out for basically buckling modes which have a buckling factor lower than 10. Imperfections have been added in the model by using the deformed shape of the buckling mode for the buckling modes which have a buckling factor lower than 10, but just one at a time. Yeah, we can see here the buckling mode, the first buckling mode under wind load. So the structure works as a series of almost independent arches. So it's not really subject to global buckling, and it's not really subject to snap-through either. So as a conclusion on the structural system, we have arches that are rectangular hollow sections from 500 millimeter deep to 350 millimeter deep. They transfer the forces to the edge beams through compression and bending, and tension as well if we have uplift. Edge beams are pentagonal hollow sections. They integrate the gutter. They spread the loads back to the support. Longitudinal beams are I-beams. They provide a restraint to the arches. I will explain later. We're supposed to provide support for the cushions. And bracing are made of tension rods, and they provide a restraint to the arches as well. Some images of the construction. We can see that the gutter was used by the workers as a working platform, which was very useful. And images of the inside. So we saw that the geometry of the roof is reasonably complex, but it must be buildable in the end. And it's very important to be able to communicate simply this buildability to the fabricator, especially that, well, with Thailand we had a little language issue. So it was very important for us to be able to simplify with really basic geometrical principles so that the fabricator could understand how to fabricate and build a structure. For the arches, that was reasonably simple. The arches are planar and decomposed into a series of arcs. We've decided to use build-up sections, so the rectangular hollow sections are made of plates, which means that the flange can be rolled and the web can be CNC cut. The edge beams are pentagonal sections, as I said previously, and we had three main constraints on the edge beams. The first one was that the gutter bottom should always be horizontal. This was to enable installation of the rainwater downpipe outlet system, and this is a constraint that was given to us by the rainwater downpipe outlet contractor. The H-beam plates should be buildable, which means that they should be made of cylindrical surfaces, sorry. And the last one was that the intersection of the H-beams at the corner of the roof should be aesthetically pleasant. The section that we chose for the H-beam and the geometry that we chose for the roof did not really facilitate our life on that part. The H-beam center lines are curved and planar. We can see in red here the H-beam plane. And on the section, there is only one plate that is parallel to the plane of the beam. And we can see there is no plate that is perpendicular to the plane of the beam. So the plate that is parallel to the plane of the beam is reasonably simple. It's just planar. But the other plates, which are not parallel nor perpendicular to the beam plane, would be conical. Conical surfaces in steel can be fabricated, but it's a bit more difficult and it's a bit more costly. So we didn't want to do that, and so we had to regenerate all the plates with cylindrical surfaces. This was done in two phases. The first phase consisted in studying the intersections and the appropriate H-beam section by using conical surfaces. So this enabled us to agree on the principles of the H-beam sections. We had decided to use pentagonal sections, but ultimately we could have all the shapes of pentagons. So this enabled us to agree on the plates' dimensions, the angles of the plates, and then to agree on the intersections that we wanted to have. So we can see here a study on the 4 intersections of the H-beam that we did to have something that is reasonably pleasant. Once this was done, we could regenerate all these plates by using cylindrical surfaces. So we did that by using a series of projection and approximation into arcs. So if I take the example of the gutter bottom, what we did is we took the gutter bottom plate, which is this little one, oriented perpendicular to the main curve, and we drew a vertical plane that is basically kind of normal to this section. We projected the main curve on the vertical plane. The new curve obtained on the vertical plane was then approximated into different arcs, and then the arcs were extruded into cylindrical surfaces, and the plates could just be redrawn on the cylindrical surfaces. So these steps were repeated for each plate and each H-beam, and of course, because of the projection and the approximation into arcs, we had small deviations from the initial conical surfaces that we had done. So to ensure that we have a perfect intersection for each H-beam, we established a parametric model in order to be able to move the H-beam points until we have a satisfying result. So for example, in black here we have the points of one H-beam, in red the points of the other H-beam arriving at the intersection, and we just moved the points on the parametric model to get a perfect intersection. So I said earlier that we had 3 main constraints on the H-beam. So first, to have cylindrical surfaces. Second, to have nice H-beam intersections. And the third one was to have a horizontal gutter. So life would be too simple if we managed to have the 3 of them perfectly. So I just showed that we achieved the first 2, and the third one was geometrically impossible with reasonable lengths of plates to achieve. So we used programming to detect the deviations of horizontality in the gutter plate and decide if these deviations were acceptable or not. For us, these deviations were within the tolerance of fabrication of the steel and the tolerance of the rainwater downpipe outlet system installation. So they were considered acceptable. And programming, it also enabled us to extract all the relevant information for the fabricator, which means basically for the plates of the edge beam, the radius of curvature, and the orientation angle of the plates to the cylinder principal curvature. As we can see on this image, the plate is part of a cylindrical surface, but is not necessarily oriented in the principal curvature line of the cylinder. So we had to give the angle to the fabricator. Here is an image of the fabrication of the edge beam, where we can see the plates being welded together with some internal stiffeners as well. And another image where we can clearly see the gutter basically here. So as a conclusion, an extensive study on the geometry of the roof and the structural system was done, and that enabled to find, to try and best integrate the roof in its environment. We think that we managed to achieve an elegant roof that is providing an aerated and relaxing space for the pedestrians. One thing to note is that at tender, the ETFE contractor proposed to use long cushions because they were reasonably confident that it would not pose a problem in case of damage of the cushion. So we didn't have further time to restudy, but with more time we could have studied alternative options in order to remove the longitudinal beams and have an even lighter looking structure. One image of the completed roof and another one. Thank you.
Thank you very much, Catherine, for this amazing talk. Who would like to ask a question? That edge beam is just incredible. Some questions? Yeah, please. Should you? I don't know how this works. You're going to do it?
This H-beam, the build-up section, how did you compensate with the shrinkage due to the welding? It has a lot of welding. How did you compensate this? The geometry is very complex, though. Yes.
Yeah, it is very complex, and I have to say this is the amazing work of the fabricator. That so it's ITD, it's Italian Thai development. It's a big fabricator in Bangkok, and they are pretty amazing for steel structures, and they really know how to play with the steel. So they manage all that part.
Okay. Are there any other questions? Mm-hmm. I'm going to ask a question. So you talk a number of times. I mean, I'm amazed by the complexity of the edge beam. I won't ask any questions about that. You talk a few times about the structure being elegant, and also when you present the three options, I think you present, oh, this one is obviously not very elegant, and this one's much more elegant. How do you make those choices? It's a bit subjective. But I'm wondering, how do you have these conversations, or what do you talk about when you talk about this is more elegant than this?
It is completely subjective, and I have to say we were quite lucky because we had the total freedom from both the client and the architect to do whatever we wanted. So it was more about internal discussions on how the structure looked like. Well, there are some architects in the team as well, so basically that helped to try and decide if this was reasonably elegant or no. And then, well, some discussions with the client to see if they were happy, but that's totally subjective,
yeah. But I think there are some rules or like things that you look at, for example, the number of elements, whether they're all aligned. Did you discuss things like this? Or?
Yeah. So we, basically, what we try to have is a smooth surface. So because of the geometry, we wanted to have something perfect, made of either a rotation, translation, or homotesy. But with the shape of the roof and the supporting conditions, this was not possible. So almost a half of the roof is a rotation surface. And basically, the rest is like almost one, but it was just tweaked by hand to avoid having kinks, to be able to reach the supports, and yeah, it was a lot of tweaking by hand to make sure that things remain smooth, basically.
Okay, all right, thank you. Yeah, we have another question there.
Yeah, then right there. Yeah. Okay.
The microphone.
Okay, over there. Yeah. Oh, sorry.
Yeah, thank you for a very interesting presentation, and it builds on to Sigrid's question and to how you answered it. So you kind of tweak things. So then the question is, was it all done in a digital tweaking, or did you actually work with physical models to kind of look at it and to turn it around and to go under it and above it, and yeah?
So we used mainly Rhino to do all the 3D modeling, and well, basically Rhino is quite helpful to go and look at it from below. But what we've done at some point is we printed a 3D printed model so that we could show it to the client and help him understand basically how it would look like in reality, because sometimes clients don't really realize how it is if we just show him an image from the model. So we kind of used the two, yeah.
Yeah, I think it's good because like although Rhino is helpful, when you, in the presentation, when you talked about how one of the options was eliminated because it had a kink, well, it was not possible actually to see the kink.
Yeah, I know.
So,
yeah.
so I think working with two, I think was really good, yeah. Thank you.
Thank you.
Okay, well, please join me in applauding Catherine for a great presentation, but also for the prize that she won. Congratulations.